Welcome to Crash Concepts, where the economy, energy, and the environment are explored. Up next, fresh ideas and insights into the factors that are driving the world and shaping your future. Presenting information you can't afford to live without, here's Chris Martenson.
Welcome to this Peak Prosperity Podcast. I am your host, Chris Martenson, and today we are joined by Lika Guhathakurta, NASA astrophysicist and program scientist for the Stereo mission and lead scientist on NASA's Living with a Star initiative. Lika works as a scientist, a mission designer, instrument builder, teacher, spokesperson for NASA's heliophysics division, and I've asked Lika on the program to discuss the science behind coronal mass ejections, otherwise known as CMEs. Now, a massive CME called the Carrington Event occurred in 1859, and it disabled much of the world's then new telegraph system. What would be the effect if a similar event happened today? Is our much more technology-dependent world more or less vulnerable? How likely is such an event? And should we be more prepared than we are, or are we okay given the probabilities involved? Lika, I really appreciate your joining us today.
Thank you.
So, let's start at the beginning. Please describe a coronal mass ejection, or CME, what it is and what causes them.
We actually start with our star, the sun. And so, we actually live in the outer atmosphere of our star. And I don't think most people recognize that. The sun is continuously losing material in the form of a low-density wind. These are not wind in the traditional sense, but really electrons and protons blowing out from the sun. This is the outermost atmosphere, otherwise also known as the solar corona. Sun is a very ordinary star. So from an astrophysical point of view, there's nothing very distinct about it. But believe it or not, this is the star that has made life possible here on Earth. And we still don't know. We are still looking for life out there. Now, what makes sun interesting from the point of view of solar system or for, inhabitants on this planet Earth? Sun is an ordinary star, but it's a magnetic variable star. And so what that means is that the sun, like Earth, has its own magnetic field. It generates a magnetic field that varies with time. And it varies as a cycle. Every 11 years, that's the most distinct cycle, the solar magnetic activity goes from being very high to very low. Kind of like, terrestrial weather scale, it would be El Nino, El Niña kind of concept, maximum, minimum. And so when we have solar maximum, when the magnetic activity is strong, we have what's called on the surface of the sun, the yellow ball that we can see with unaided eyes, dark region appears. And these dark regions are called sunspots. Now, these regions are dark not because they are not hot, but because they are a little bit cooler compared to the rest of the surface. And the reason they are a little bit cooler is because they harbor intense magnetic field, and this magnetic field essentially inhibits, transport of energy from below to the surface. So that's kind of where I would like to end and then launch into CME. And so these sunspot regions, which are also called active regions, often are the regions where we will have a solar storm, which otherwise in our technical language we would call solar flares or coronal mass ejection. Now, a solar flare is a very intense release of magnetic energy. And this is when, it is very, very sudden and very intense and very bright. And so the Carrington event that you were referring to was actually a solar flare that was observed way back in 1859 by Richard Carrington. And I'll come back to that. But during a solar flare, we can also have other solar storms happening side by side in conjunction, and that would be a coronal mass ejection. And a coronal mass ejection is that when we have, if you actually watch NASA satellites, movies from them like Solar Dynamics Observatory or so, you will see that there are large loops, rising above the photosphere, which is that yellow ball. And these magnetic field lines will eventually, with time, get twisted and knotted and sheared, much like if you take a rubber band or a slinky and keep twisting it, it will eventually tear open. Same thing happens with the magnetic field lines, and so they eventually tear open just from the pressure built up. And then when that happens, what is released in the process is a billion tons of cloud in the form of magnetized plasma. Now, plasma is otherwise the fourth state of matter. So it's not gas, it's not liquid, it's not solid. It is closest to sort of gaseous liquid state, but it is not neutral. It is electrified. So all the atoms in plasma lose, their outer electrons, and the atom becomes ionized. So what you have in plasma is a soup of electrons and protons. And that's what is released along with the embedded magnetic field in a coronal mass ejection. A coronal mass ejection can be a huge, in terms of latitude and longitude. It can engulf our Earth and many more Earths in it. They can be really massive in size, and they also expel a huge amount of matter and energy, which then starts propagating through the interplanetary medium. Interplanetary medium is the distance between Sun and Earth, and it's about 93 million miles between our planet, Earth, and the Sun. And so these materials can be released, at a speed of as low as 20, 30 kilometers per second to as fast as thousands of kilometers per second. So it starts moving through the interplanetary medium, running into other material that exist already, creating shock waves, much like we do on our planet, in the ordinary weather sense. And then these will come impinge on Earth's magnetosphere. So I'm going to stop here. But this is kind of what a coronal mass ejection is.
It sounds very descriptive. So there's this ejection of stuff, and that stuff is magnetized plasma, this fourth state of matter. So we have some charged particles coming at us at anywhere from 20 to 30,000 kilometers per second to maybe hundreds of thousands of kilometers per second. And
not that much, no. It can be as low as, sort of 100 kilometers per second.
Okay, yep.
As high as 2,000-3,000 kilometers per second. And then the most ordinary kind of garden variety CME will be of the order of 400-500 kilometers per second.
Okay, and so when this is released from the sun, and it's related to the amount of magnetic activity, is that fair to say?
It is very much so.
Okay, so when we're at a solar minimum, we might expect fewer of these, and when we're at a solar maximum, we would expect more of these, and we detect the solar maximum through sunspots, I guess, historically. The more sunspot activity would be a solar maximum in terms of magnetic activity, and then the opposite would be a minimum. Is that correct?
Absolutely. Okay. Although I kind of want to draw your attention, because we are talking about solar cycles, these are all very important concepts that people always don't, think about. And so while the frequency of solar storms, coronal mass ejections typically tend to go down during solar minimum, the intensity of such coronal mass ejections don't. As a matter of fact, most of our most severe solar storms tended to happen during sort of weak solar cycles and during the declining phase of a solar cycle. So we are talking about frequency. During solar max, you can get, of the order of 3 to 4 CMEs per day, whereas during solar minimum, it could be a CME every few days. And that's kind of the difference.
All right, so the frequency is dependent on the minimum maximum, but the intensity, is that independent, or do you tend to...
It is quite independent.
Okay.
It really depends on the nature of the magnetic field configuration that eventually releases the material, and that is the cause behind a solar flare or a coronal mass ejection.
All right, so the Earth is somewhere in the sun's atmosphere, as it were, and this is a very active creature, this sun of ours, and every so often tosses out some particles. And when it tosses those out, how would you know if you were in the way of those? I mean, the sun's a sphere, right? And I assume this is these ejections, are they happening anywhere on the sphere of the sun, or does the sun have an orientation it tends to send out more in one direction than another? And where are we in that directional flow, if there is one?
Well, actually, these are all really very good questions. Yes, sun is a sphere, and these storms happen in terms of latitude. There is a spread, but in terms of longitude, it happens all over. So in terms of latitude, we don't get solar storms, coronal mass ejections from the poles of the sun, north and south poles. They are more kind of in the equatorial and mid-latitude zone is where we get these storms from, not from the poles, but it can come out from any direction in terms of longitude. And so what's really interesting is that one of, my mission, for which I'm the program scientist stereo, where we sent 2 spacecraft, okay? These 2 spacecraft are actually in the same orbit as planet Earth, going around the sun, but one is leading Earth and one is lagging Earth. And so they have drifted away from our planet, and they reached opposition, and now they are actually able to view the far side of the sun. So in some ways, we have, say, 3 points. We have all our satellites in the sun-Earth line, and we have 2 stereo spacecraft kind of in opposition going behind, because these 2 spacecraft are drifting at a rate of about 22 degrees per year. And so now we can see the front side and the far side of the sun all at once. And we are downlinking, bits of data, just small amounts of data, just to see what's happening on the far side of the sun. And to me, that is just pretty unbelievable. Up until February 2011, which is when these stereo spacecraft went into opposition to give us a full view of the sun, we were not able to see the far side of the sun with any man-made object. And we not only see it with our observatory, what we have done is we have kind of created app, which is called 3D Sun or i3D Sun, meaning interplanetary 3D Sun. And you can get this on iPhone, iPad, I believe also on Android, and you can see what the sun is doing at any time. It's like the sun in the palm of your hand.
Well, that's fantastic, and that's only since February 2011?
That's when we were able to see the full sun in totality. And, it's not going to last forever, of course, because the stereo spacecraft are drifting. Right.
Okay. So that's just fantastic. So what are we learning from that? And what I'm interested in here is as well is the idea of how often it is that the Earth might be in the path of, well, let's just say of these coronal mass ejections that are happening. What's the probability of the Earth being in the path of one of these?
The probability is quite high. So during solar maximum, since we have, of the order of 3 to 4 CMEs per day, so you can, of course, imagine that 1 or 2 will be directed at Earth. Now, remember, any CME that is on the front face of the sun, since these are really sort of massive in terms of latitude and longitude, that even if it is not directly sort of square on towards Earth, it is going to impact Earth, because these structures often are much more massive than the Earth itself. But outside of that, and so the probabilities that we have calculated, 3 to 4 CMEs typically have been looking at the Earth-directed CMEs. How frequently do we see these? How frequently do they impact our geospace environment? This is pretty routine. We are observing it. We are measuring its velocity. We are measuring its density. We are kind of trying to understand the magnetic topology. And so we are, providing some level of understanding towards forecasting, these events, their speed, and when they will arrive on our Earth's geospace environment. What's real interesting is that when we talk about extreme events like the Carrington event, we are really not sure when one of those events might occur. Typically, those large extreme events are something that we categorize as, high impact, low probability events. You can say it happens every 100 years, every 150 years. But remember, so far our data has been only from the front face of the sun. We do not know what's happening on the far side of the sun, or we haven't had sufficient data to determine that. So our probability to that extent is incomplete, and we are recognizing that even more when we look at the stereo observations. For example, just last year in July, one of the stereo spacecraft, Stereo A, which is ahead of our planet Earth, actually witnessed coronal mass ejection, which was very, very powerful, comparable to the event that was seen in 1972 during the in between the two Apollo era. And scientists are actually really, because we have the data, but it wasn't Earth-directed. It was really captured by stereo, and we have the data. They're trying to figure out if that event was actually directed at Earth, what would we be facing? So there's a lot of understanding going on with these new observations.
Well, let's talk about this for a second, the potential impact. From what I've gathered, a coronal mass ejection is tossed out into space. It spreads a little bit like a shotgun blast might, and the Earth will be somewhere within its aim of sight, as it were. And if we're directly lined up and there's a lot of particles coming at us, we might record that as a very big event, maybe as high as a Carrington class at some stage. Is that fair? These things are tossed out and then they spread and we're somewhere in its cone of influence, which might have a real variability from edge to edge compared to the center.
Mostly. So what I'm going to say. So let's start what happens when these particles actually arrive at Earth.
Okay.
So from the sun, we have a good understanding because we can also see these with our satellites. We are measuring them. Huge amount of mass, momentum, energy coming at Earth. Now, a solar storm always does not lead to a geomagnetic storm. What do I mean by a geomagnetic storm? A geomagnetic storm is when a solar storm is actually able to penetrate into Earth's geospace, into Earth's magnetosphere. And, most of the time, Earth's magnetosphere is able to sort of deflect whether the coronal mass ejections or, high-speed solar wind, etc. But if the magnetic orientation of the coronal mass ejection is such that it can actually connect with the magnetic field of the sun, that's when these particles actually penetrate into Earth's magnetosphere and deposit all of that energy. And that is something today we cannot predict just with our model. The way we predict this is with observation. So we have a satellite called ACE, Advanced Composition Explorer, which is about 1.5 million kilometers upward from Earth towards the sun. And that's where it actually measures in situ, local environment of the spacecraft, the magnetic field, as well as the particle velocity, density, etc. When ACE actually determines the orientation of the magnetic field line with its sensors, that's when NOAA, Space Weather Prediction Center, who is in charge of providing essentially warning watches to the nation, issues a warning saying, whether the storm is going to be, mild, medium, severe, kind of like the way we do hurricane prediction, depending on the severity, the size of the coronal mass ejection, and the orientation of the magnetic field. So that is a very key piece. Just because we have a solar storm does not always mean that we are going to have a geomagnetic storm which will have its consequences in our geospace environment. Does that answer your question?
Absolutely. So it's not just size, it's orientation that really matters here. If it's pointed right at the Earth, these particles might penetrate. If they do, let's talk about what happens then. So what is the impact, say, on, let's go from the outside in, satellites, maybe terrestrial communications. What's the first thing that might be impacted if you had a really big event that was pointed right at us?
I think if the magnetic connectivity is made at that point, what we see are beautiful aurora, both northern and southern lights. And, that's when there is that a solar storm has led to geomagnetic storm. Now, this is the more sort of beautiful side of solar storm leading to geomagnetic storm. But outside of that, I think what this does, this geomagnetic storm really causes disturbance in Earth's magnetic field, and that disturbance causes fluctuation in current. And when and then there are solar energetic particles. So there are many things going on. You can have, all your satellites become vulnerable to single event upset from solar energetic particles, which is essentially any electronic that interacts with these particles. You can have fluctuation in Earth's ionosphere, which causes scintillation, that causes problem for communication. You can have, so communication, navigation, these are problems. High altitude aircraft, especially in the polar route, if they have communication, navigation issues, they can't fly in that zone. High altitude aircraft and crew are exposed to radiation hazards. If astronauts are doing EVA, they can be exposed to radiation hazards. Most importantly, these magnetic fluctuations that, it essentially leads to also induced ground current can actually cause significant fluctuation in our power grid. And power grid becomes quite vulnerable. And there have been occasions where we haven't had Carrington-type events, but even smaller events have led to failure or damage of transformers, which then leads to, wide-scale blackout without power, and that, life without electricity in modern day has its impact.
Oh, absolutely. We certainly saw what happened in Fukushima and the difficulties they had there once they lost their power grid and ran out of backup power for the reactors over there. Obviously, it's a very, very big deal. So let's talk about this one in particular, where the magnetic field gets assaulted or distorted. It gives us this induced ground current. Take us back to the Carrington Event in 1859. I'd read some accounts of people being able to send telegraph messages without actually having any power hooked up. I've heard of sparking, arcing, even meltdowns. What was happening there?
These currents, in fact, were so powerful. So your atmosphere almost is getting electrified in this case. So we have not, in real life, beyond 1859, experienced, Carrington type event, which was so powerful that, normally the northern and southern lights are essentially in very high latitude north, high latitude south. In case of the Carrington event, we could see the northern and southern lights down to Bahamas. So the magnetosphere of Earth is just compressed on the day side and extends on the magnetotail night side, and that is what is causing this tremendous fluctuation. In some sense, you can think of the early telegraph lines of the 19th century. It's like the Victorian equivalent of internet today. If we had a severe kind of solar storm of the Carrington variety, you can imagine that your internet will not exist. Not because the internet will catch on fire, but if you think of how satellites control, many of the sort of signals, if you think of how you have power that is required for the internet to operate, some of these things will just go away if we had a massive storm of the variety of Carrington event. What we, I think, don't fully appreciate today is that how dependent our life has become on technology. And a lot of these technologies are no longer radiation hardened, and so they are actually vulnerable to not only extreme storms, but even medium or mild storms.
This technology meaning satellites all the way on down to our power grid?
Well, power grid is sort of a different problem. I would say satellite components, for example. When you have such a massive electromagnetic disturbance on Earth, anything that is, operated by electricity is vulnerable to this fluctuation. Anything, so your railway switches, your pipeline, things that you don't even associate with space weather, you find will be really susceptible to this massive onslaught of the magnetic disturbance in Earth's geospace.
Now, Lika, you mentioned before that Stereo had observed a really big event that we would have missed. It happened fairly recently. It might have been as big as the 1972 event, and that there had been some studies or analysis around, well, what would have happened if that pointed at us? Are you familiar with that? What would have happened if something...
This study is not complete. It's not in scientific literature, and so scientists are actually now using real data and putting it in their model to extract, what kind of conditions might we have experienced. Now, the induction of ground current, for example, depends not only on the storm itself, but also the local conditions of the ground conductivity of a given region. So not every region will face the same thing. So there are just many aspects to these analyses that we are still trying to bring together in the form of data and understand.
Sure. Now, in general terms, understanding that local mileage will vary because it's like fluid dynamics. I assume there's just
right.
a lot of intervening forces, and so it will not be an evenly spread event. It'll be concentrated in some areas, minimized in others. So, but generally speaking, if we were looking at, say, this induced ground current, and we were thinking about the power grid, What are the possibilities there that could have happened if the 1859 or this most recent one or even the 72 event, if those really come along? Are we relatively prepared in terms of hardened transformers in particular is the component I guess I would be most worried about? But what are we looking at there, and what are the concerns?
I think both NORC and FORC are very aware of this possibility. We have had an event in 1989, which was the failure of the Hydro-Quebec power company. And so people are very familiar with what can happen. Now, are the power grids sufficiently hardened? I guess I won't venture to answer that question. It's kind of out of my area of expertise. You can read up and you will know. But what I will say is that the kind of warning that, we are providing via NOAA through NASA science observations and analysis is very useful for the utility companies. And the basic kind of bottom line is that, you kind of operate, you develop a strategy to operate the system in a conservative mode so that it can handle sudden surges of current and voltage without overload. And so, NOAA is able to issue this warning once it gets that measurement from ACE, and it's of the order of 20 to 30 minutes. But before that, even when there is a coronal mass ejection happening, it takes anywhere from your 12 hours to 3-4 days for that coronal mass ejection to arrive, and then so power companies are given that information, so people can begin to take mitigating steps.
So if we record a big one, we might have a number of days to sort of prepare for it or get ready for it, and then ACE will detect if it's really bad, and then you'll have 20 to 30 minutes to put those plans into effect if you thought it was pretty serious. And all the power companies are this is something that's clearly on the radar screen. Is that right?
Absolutely.
Okay, fantastic. So, what precautions, if any, are there any concerns for an individual person living here, maybe listening to this, who doesn't run a power company, just lives at home? Is there any sort of concerns that they should be aware of? Is there any chance that there's any of this ionizing radiation coming down? You mentioned it's a hazard for high flyers, right? Pilots, astronauts, is there?
It will be important for space tourism, but not for us who are actively on ground level. But the kind of nuisance that they might experience is iPhone signal going on, your GPS devices working erroneously. Those sort of things is something we probably will feel and do feel from time to time.
Yeah, so we might experience power loss fluctuations, a little disruption of communications, and some very nice auroras. Is that about it?
That's about it. When we are, in some ways, if you are dependent on GPS device for whatever reason in the transportation sector, for example, that's a big loss. So it depends on what sector you come from, where you would know how severe the loss is. These are not necessarily life-threatening, but it depends on the situation.
Well, and certainly you mentioned the largest threat, which is unknowable, is the degree to which we've become technologically dependent. And essentially, we can't really know what the impact of such an event will be until it arrives and we see what happens. It's hard to run that experiment, I assume.
It's absolutely, other than, writing fiction.
Right. And so you've mentioned an event in 72 and 89. They sound like they're relatively frequent in a human lifetime. They're not like a super volcano or something that happens, every few 100,000 years. This is a fairly regular part of living within the sun's atmosphere, and we would expect them to continue to occur, right?
Yes, and so the 72 and 89 again were much smaller in scale compared to the Carrington event.
Mm-hmm.
We have not seen anything like a Carrington event.
So that was a fairly unique event in our recorded history.
That still remains fairly unique from the kind of data that we have.
Yep. And so I'm going to assume that one was pointed right at us when it let loose, and we were pretty much dead in its sights.
Absolutely. In fact, Richard Carrington, he was projecting the sun onto a paper, which is where he saw in the sunspot region these immensely bright two white dots, which eventually was the first visual sighting of a solar flare. Rapidly changing. He was so excited he called for another witness. And in about 60 seconds, these flares had changed configuration, becoming, of course, less threatening. I mean, a solar flare is, as I mentioned, very rapid and a huge amount of energy.
All right. So beyond being prepared for a surge or loss of electricity, should such an event come, and I guess people could take some precautions, maybe flip critical or sensitive electronics on or off if they thought such a thing was coming. It sounds like we're just pretty much at the mercy of what comes, and we'll see what happens when another one happens. And in terms of likelihood, how likely is it that we would see what we might consider a disruptive CME in, pick a time frame, I don't know, the next 20 years?
It really is very difficult to say. I think what we are witnessing is actually that the solar cycle is weakening in intensity. And the last solar minimum was actually a very long solar minimum. So indications are that solar cycle is actually decreasing in its intensity. Does that mean that we cannot have a powerful coronal mass ejection? Absolutely not. As I indicated, most of the strong solar storms came from weaker solar cycles on the declining phase of the solar cycle. So I think we have to be ever vigilant. We never take our eyes off of terrestrial weather. When hurricanes are forming, it is the same thing. We have to continuously monitor the sun. We have to understand, the physics of it with sufficient understanding to be able to develop models to predict it. We are getting better at that. I think one final thing I want to say is that something that we have not paid maybe a lot of attention to is high altitude aircraft that are flying polar routes, crew and passenger on high altitude aircraft. These people, depending on how often you travel, these people are subjected to radiation. And while in some countries, they have begun to kind of measure this, out here we haven't started doing that yet. But there's a lot of work going on in the aviation world trying to understand the exposure to radiation. And this will become even more important as, the space tourism industry flourishes.
All right. Well, I'm certainly fascinated. And if I wanted to track for myself, could I go to the NOAA website and see either their warnings or the ACE data itself in something close to real time? Or how would you track this if you were interested?
Yes, absolutely. If you go to the Space Weather Prediction Center website, which is in Boulder, Colorado, you will have a lot of information there, from the current conditions to long-term forecasting, medium-term forecasting. Right now, what's happening is just lots of good information. And you can go to NASA websites for seeing some of the fabulous imageries and models that we have developed from this data.
Well, fantastic. That is just absolutely fascinating work. You've got a great career. I'm jealous. We've been talking with Lika Guhathakurta, and Lika, thank you so much for your time. I really appreciate it, as I'm sure everyone does listening to this.